Welcome to the next video in the Universe series on Beyondearth channel. In this video, we will learn how humans have been able to discover so much about this universe. Whenever humans have looked up at the sky, one question has always arisen in their minds. Where am I? The desire to know about the universe has always been in the hearts of humans. However, humans have never been able to fully understand the things shining in the sky because we did not have any instrument through which we could observe the sky properly. Humans have always seen the sun, moon, and stars moving in one direction, which led them to believe in the geocentric theory, meaning that the entire universe revolves around the Earth. But then, everything changed with the invention of the telescope in the 17th century. On January 7, 1610, Italian astronomer Galileo Galilei pointed his homemade telescope towards the brightest star in the sky. Galileo was amazed to find that what we thought was a single star was actually a group of 4 stars. A few days later, he observed that instead of 4 stars, 5 stars became visible. After observing this group for some time, Galileo realized that these 4 small stars were orbiting a larger star. At that moment, Galileo was actually observing the planet Jupiter and its 4 moons. Later, Galileo also observed the phases of the planet Venus and found that it orbits the Sun. This clearly meant that the entire universe does not revolve around the Earth. Galileo's discovery proved the famous geocentric theory wrong, after which the heliocentric theory gained prominence. This theory was presented by Nicolaus Copernicus in 1514. According to Copernicus, the center of the universe is actually the Sun. And the entire universe, including the Earth, revolves around it. Copernicus even depicted a picture of the heliocentric universe in his book. On one hand, some scientists were trying to understand the shape of the universe, while on the other hand, some scientists were trying to learn about the vastness of the universe. To do this, it was essential to know the distance between celestial objects. Humans have always measured the distance between objects, but they have also known that the sun, moon, and stars are very far from us. So, how could we measure the distance of things that are beyond our reach? Early scientists found a great method to measure these distances. Parallax. When we close one eye while looking at an object and then close the other while opening the first, we see the object moving right and left. This effect is called parallax. If we know the distance between our eyes and the movement of the object, we can use basic geometry to calculate the distance to the object. However, the farther an object is, the harder it is to detect its movement, which is why we have to increase the distance between our eyes. The Greek scientist Hipparchus first measured the moon's distance using parallax in the 2nd century BC. Since the moon is very far from us, Hipparchus had to observe it from 2 different locations 1,300 kilometers apart. But after measuring the distance to the moon, scientists found themselves in a dilemma. The planets were so far away that it was impossible to measure their distances with the parallax method using the technology of that time. Scientists were now at a loss. They either had to find a new method or wait for an invention that would help them learn more about the universe. This wait stretched for centuries, and finally, in 1608, the invention of the telescope gave scientists another opportunity to understand the vastness of the universe. The same telescope that Galileo had used to disprove the geocentric model just 2 years after its invention. In 1672, French astronomer Geovanni Cassini and his assistant observed the planet Mars from 2 different locations using a telescope, and they succeeded in calculating the distance to Mars through parallax. Now, measuring the distance to planets became easier. But when it came to measuring the distance to stars, scientists were once again stuck. The distances to stars were so vast that the parallax method had failed. It seemed impossible to measure the distance to stars. But then, in 1838, German astronomer Friedrich Bessel introduced a new method of parallax. Friedrich proposed that if we cannot detect the movement of stars from Earth, why not move the Earth itself? For parallax, he suggested making one observation today and another observation 6 months later, when the Earth has moved 300 million kilometers away. Using this method, Friedrich Bessel calculated the distance to the star 61 Cygni in 1838, which was 107,892,370,320,000 kilometers. Keeping a record of such large numbers was difficult for scientists. Light travels 94 trillion kilometers in 1 year. If this distance is called 1 light year, then the distance of 61 Cygni becomes 10 light years, which was much easier to record. From 1838 to 1910, scientists used Friedrich's method to create a rough image of the universe, with its width being about 100,000 light years. This image made one thing clear: our Sun is just like other stars, and just as planets revolve around the Sun, our Sun also revolves around the center of this vast universe. With this information, the heliocentric theory also came to an end. But in 1912, 2 discoveries were made that later led to a new theory, which still stands today. Scientists could now measure the distance to stars using Friedrich's method, but this was still very difficult. And this method could only measure the distance to the stars that were closer to us. This was the limitation of the parallax method. To measure greater distances, scientists needed a new method. But why? Even after knowing the shape and size of the universe, why were scientists still searching for a new method of measuring distance? This was because scientists had discovered something else in the universe apart from stars. They found beautiful objects, which they named nebulae. Some of these nebulae had their distances measured, but there was one special type of nebula, the spiral nebulae. They were far enough that their distance could not be measured. Looking at these spiral nebulae, it appeared that they were clusters of many stars. In 1912, American astronomer Vesto Melvin Slipher used spectroscopy to try to understand what these nebulae were made of. Just like how sunlight is split into different colors to form a rainbow after rain. In spectroscopy, the light of stars is split into different colors and observed. Upon close inspection, black lines are visible in these colors. These black lines act as a barcode to tell us what the star is made of. During spectroscopy, Vesto Slipher noticed something strange. In the spectra of most spiral nebulae, the pattern of black lines shifted to the red side rather than the normal position. This phenomenon is called redshift in spectroscopy. It meant that these spiral nebulae were moving away from us. Just as the sound of a car approaching becomes higher and that of a car moving away becomes lower. In the spectrum, blue light has high energy and red light has low energy. The redshift of the black lines was a sign that these nebulae were moving away from us. But we needed to measure the distance, and spectroscopy could not help in measuring the distance. In 1912, another American astronomer, Henrietta Leavitt, was studying a type of star called variable stars. The light of these stars varied over time. Henrietta found in her study that many of these stars were regularly changing their brightness, or we can say they were pulsating regularly. Further study led Henrietta to the conclusion that there was a deep relationship between these stars' pulsation and brightness, meaning that by studying their pulsation, we could find out their actual brightness, regardless of how far away they were. Henrietta called these stars Cepheid variables. These 2 discoveries in 1912, the Cepheid variables and redshift, would change everything in the next few years. American astronomer Edwin Hubble found Cepheid variable stars in spiral nebulae and compared their brightness with actual brightness to measure their distances. In 1924, Edwin Hubble revealed to the world that the distance to the Andromeda Nebula was 2.5 million light-years. But our universe is only 100,000 light-years wide, so how could the Andromeda Nebula be 2.5 million light-years away? Edwin Hubble's discovery changed our entire perception of the universe's size. These spiral nebulae were actually galaxies, just like our own Milky Way galaxy. Andromeda is one of the closest galaxies to us, but there are trillions of galaxies in the universe, some of them billions of light-years away. Now, everything was clear: our Earth revolves around the Sun, and like other stars, our Sun revolves around the center of the Milky Way galaxy, and there are trillions of galaxies like ours in the universe. But wait, there is more. Edwin Hubble was about to uncover one more great secret of the universe. In 1929, Hubble compared the distance of galaxies with their redshift and found that the farther a galaxy was, the faster it was moving away from us. This meant that the universe was expanding, just like everything spreads out after an explosion. But the speed at which the universe was expanding was astonishing, millions of kilometers per hour. This discovery suggested that something very big must have caused this rapid expansion. Or perhaps the universe itself began with a huge explosion. Scientists named this theory the Big Bang. While the Big Bang theory explained the beginning of the universe, another theory called the Big Crunch explains that the universe will end when gravity finally pulls everything back together. In 1964, 35 years after Hubble's discovery, two American radio astronomers, Arno Penzias and Robert Wilson, used a 6-meter radio antenna to detect radio waves coming from the sky. But they started hearing a faint noise from all directions of the sky. Despite all their efforts, they could not eliminate the sound. Temperature, time of day, or seasons had no effect on it. They unknowingly detected the cosmic microwave background radiation, the afterglow of the Big Bang. Just like how we can hear the sound of an explosion long after it happens, the Big Bang emitted so much light that today, after 3.8 billion years, we can still detect it in the form of microwaves. The cosmic microwave background, CMB, is the sound we hear when we switch channels on an old TV or radio. When a star explodes, it becomes brighter than an entire galaxy for a short time. This explosion is called a supernova. By 1990, a type of supernova, Type 1a supernova, had been discovered. Type 1a supernovae could also be used to measure distance like Cepheid variable stars. The galaxies that were billions of light-years away from us appeared so small that it was impossible to observe individual Cepheid variable stars in them. To determine the distances of such galaxies, Type 1a supernovae were used. Since a supernova becomes brighter than the entire galaxy, it could be observed even from trillions of light-years away. By 1990, we had learned that the Big Bang occurred 13.7 billion years ago. But what about the Big Crunch? When would the universe start its journey in reverse? In 1998, American astronomer Saul Perlmutter and his team measured the distances to galaxies billions of light-years away and found that the universe was expanding even faster than before. This was a discovery that left scientists stunned. Could it be that the Big Crunch would never happen? There must be some hidden force in the universe that is pushing it apart. This force, which has always been around us, was only discovered in 1998. To this day, we still don't understand what this mysterious force is. As for the size of the universe, it is expanding faster than the speed of light. This means that the light of some parts of the universe will never reach us. We will never be able to see these parts of the universe, nor will we ever know just how big the universe is. This is why the term observable universe is used to describe the part of the universe we can see. In the next video of the Universe series, we will dive into the Big Bang. Subscribe.